So for an example of using the tension force, I want to consider a case of an object hanging from two ropes as shown in the slide there. The real life example, if I use my fishing rod again, would be something like this. So we have this object getting held in place by a pair of ropes, and those two ropes might be at different angles. Somehow all the forces must be balanced with each other in order to let this object hang stationary. And you can see if I do kind of different things with it, I can make that angle change. So somehow the angle has something to do with what the ropes are doing. So let's solve an example like that. So we have here a block hanging from two ropes that are tied to the ceiling, and one of them makes a 60-degree angle with the ceiling, one makes a 30-degree angle with the ceiling, and the question is, what are the tensions in those two ropes if the object is going to be held stationary? Okay, so as always, go back to the beginning. What is step one here? Draw a free body diagram. First, we need to organize our thoughts with the diagram. So now we go through what are the possible forces that might be relevant here. We have the gravitational force for sure, because this object is, the reason it's hanging downward is because of gravity. And then we have tension forces. Since there's two ropes here, there's going to be two different tension forces. And the two tension forces are going to be parallel to the two ropes. Okay. So if you want to, you can kind of overlap them with, I'm trying to draw it identical to the direction of the rope, but we like to move all the forces to the center of the diagram just to make it a little bit easier to see everything. And there's a horizontal line just to make sure we know what all the angles are. This is going to be the gravitational force here, mg. The mass of this object is going to be 10 kilograms. And then the two tension forces, I need to give those names. So let's just call them T1 and T2. So we'll make that one T1. We'll make this one T2. And the direction of the thing is going to be the same direction as the rope. So this one is at a 60-degree angle from the ceiling. So that would make this a 60-degree angle by alternate interior angles. And this would be a 30-degree angle by the same argument. So now I've got my free body diagram. I've got the vectors, magnitudes are all in there. The directions are all in there. So I've got step one of the procedure done. I have a diagram. Step two, I need to break all my vectors into components. So I need to do X direction and Y direction. And let me do this the way that I've been doing it. So I'm going to have T1, I'm going to have T2, I'm going to have mg. Make a little chart. Okay, so T1, first of all. I'm using standard XY coordinate system. So that means T1 has a negative X component and a positive Y component. I do not know the magnitude of T1, but I do know its angle. So that means the X component is going to be negative the variable T1 times cosine of 60, because the X is adjacent to the 60-degree angle. And in the Y direction, it's going to be plus T1 times sine of 60. The signs are coming from the fact that this vector points up and left, which means positive Y, negative X, up, left. And the angles are coming from visualizing a triangle like that. Okay. For T2, this one has positive X and a positive Y because it's up and right. And that's going to be T2. Once again, the X is adjacent to the angle. So this will be cosine 30. And in this direction, it'll be sine of 30. T2, sine of 30. And then the gravitational force has no X component, and the Y component will be negative. And you can plug in here if you want to. 10 kg times 9.8 meters per square second. So that would be negative 98 Newton. Okay, and I said in my setup here that this object is being held stationary at equilibrium, so it's going to have acceleration equal to 0 in both components. So now I can write down my F equals ma equations. So the x direction equation is going to be negative t1 cos of 60 equals t2 cos of 30. Sorry, be a little bit more careful. Negative t1 cosine of 60 plus t2 cos of 30 equals 0 is my x equation. 0 is coming from the fact that acceleration equals 0. And over here, we'll have positive t1 sine of 60, positive t2 sine of 30, minus 98 Newton equals 0. So those are my two equations I'm working with. And you'll notice that there's two variables, t1 and t2. So now it's just an algebra problem of solving a system with two equations and two unknowns. So you probably want to start with the left-hand equation because that one's simpler, and then solve for your favorite variable. So let's say I solve for t1. So t1 is going to be t2 times cosine 30 over cosine 60. And that would be, let's get some numbers in here. Cosine 30 divide cosine 60 equals 1.73. Okay, so T1 is 1.73 T2. Now I can plug that result into the other equation. So I'm going to have here 1.73 times T2 times sine of 60 plus T2 sine of 30 minus 98 equals 0. So now I do 1.73 times sine of 60 plus sine of 30, and that gives me 2, almost exactly 2, T2 equals 98. So again, the 2 just came from crunching all the numbers here. It happened to work out to 2. If you do 1.73 times sine of 60 plus sine of 30. And that means T2 equals 49. And now I bring that back over to the other column, and I get T1 equals 1.73 times 49, which is about 85, if I round to two significant figures. So there's my two tension forces. So again, notice that when you're solving these problems with tension forces, you're just going back once again to the basic F equals ma procedure. And there's really nothing new here. It's just more F equals ma problems with the same F equals ma procedure we've been using. There's not even any new formulas in this section. It's just a matter of putting the tension forces in the direction of whatever is doing the pulling